Hello and welcome to our webinar on NX NASTRAN Dynamics. I'm your host, Monique Anderson, and I'm pleased to introduce to you our presenters, Doug Logan, a solutions consultant, Dan Nadeau, an applications engineer, and Derek Barkey, the director of advanced engineering for Saratech. Please, just as a reminder, if you could enter all your questions and comments in the chat box to the right of the screen, we will be happy to answer those at the end of the webcast. And now I will hand the reins over to Doug, who will give you a little overview of Saratech.
Well, thank you, Monique. Hello, everyone, and welcome. Before we get into the technical portion of the presentation, I'd just like to say a couple words about Saratech. Saratech is a full capability engineering services and software company based out of Southern California. Incorporated in 2002, we now have approximately 70 employees across the U.S. and service customers across the full country. We are a nationally recognized Siemens PLM Platinum Business Partner, and we resell the full line of Siemens product lifecycle management, engineering, and factory automation software products. Saratech's core engineering staff have expertise in many specialized engineering areas, including design, analysis, prototype development, fixturing and tooling design, composite design and analysis, and additive manufacturing. We also provide training for all of these tools and services, including the topics we'll be covering today. We are very active in the aerospace, defense, oil and gas, especially offshore oil rig and ship design and structural analysis world, the automotive industry, and heavy equipment manufacturing. Saratech helps hundreds of customers like these make the most of their engineering investments, and we can do the same for you. Next slide, please. So why would engineers be interested in dynamic analysis? Well, many people are interested in examining cyclic loads as found in rotating or reciprocating machinery. In addition, simulation of short duration events, such as bumps on the road, the opening and closing of doors, hatches and valves, and so forth, need to be integrated into whole structure analysis. Today, we're going to show you how FEMAP and NX NASTRAN can be integrated with dynamic analysis. Next slide, please. I'd now like to introduce you to one of our senior engineers, Daniel Nadeau, who will be delivering the technical portion of the presentation. Dan is a mechanical engineer with a degree from the University of Pittsburgh in Johnstown. He's been with Saratech for 4 years, and his primary focuses are FEMAP, NX CAE, and NX NASTRAN. So now over to you, Daniel.
Thank you for the introduction. Hello and welcome. As Doug mentioned, my name is Dan Nadeau. I'm an application engineer here at Saratech. So today, our plan today is to talk about dynamics. So I'm going to give you a brief overview of dynamics. I'm going to show you some of the options and capabilities, and then I want to go through a quick demonstration of using some of these dynamic packages. Now, I'm not going to spend an overabundant amount of time on the theory behind dynamics, but I just want to at least give you a brief overview of dynamics. So, what is dynamics? So you'll see in the middle, you have your equation of motion. So when forces acting on a structure vary with time and or frequency. So if you're in the time domain or the frequency domain, a dynamic analysis would be required. So you'll notice now we have inertial forces. So this is what steps us into the dynamic world here. So why do you need it? So in real life, most structures are actually subjected to some sort of dynamic forces. So, an impact, some sort of frequency response. There's many dynamic things that are happening. So maybe a motor rotating, all sorts of effects. So these effects can result in higher stresses and deflections. Same in some of these regions of concern where if you run some simple static analysis, you might not be able to see that. And we'll we'll go through that in our example. So when our forces are applied are not constant, our dynamic analysis is required, and this can be in the time and or the frequency domain. So here's our basic types of dynamic analysis. We have modal analysis, we have frequency response, and we have transient response. These are the ones that we're going to discuss today. So our modal analysis is, our foundation for all dynamic analysis. So if you are doing any sort of dynamic analysis, please start with a modal analysis. It'll give you information about your structure before you even step into the next level. So doing modal analysis, we'll find out our resonant frequencies of the structure and also the mode shapes. The next step is frequency response. So the way that we think about it is a virtual shaker table. So one thing that's important about frequency response, this is in the frequency domain. So our input is a sinusoidal input. So remember, this is all based on frequency. So with this, we can get outputs such as stress, displacement, information. But remember, this is as a function of frequency. So if you remember back to our dynamic equation of motion, that is versus frequency. So even frequency response steps up even to a top level towards random vibration, where it's also based on those frequencies as well. So the next one that we'll discuss is transient response. So now we are in the time domain. So now this is something based on time. So the input is a load as a function of time. So a good example of a transient response analysis would be some sort of shock, explosion or an impact, car crash, earthquake. So something where you have something based on time. So there are some other dynamic capabilities that we'll discuss briefly. So DDAM, so underwater shock, response spectrum, maybe you are doing this seismic analysis, rotor dynamics, acoustics, flutter, and there's more. So if you want to learn more about dynamics, we do have a dynamics class. So we can even customize that to cover some more of these advanced dynamic capabilities if this would be something that you're interested in. So now I want to give you a brief overview of the packages that can be included with FEMAP or NX CAE. So here's the add-on packages to NX NASTRAN. I don't want to develop too much information about these, but I want to at least get out there and let you know what's going on. So today we're going to go through the dynamic response add-on package. So this gives you a lot of capabilities past your normal mode analysis. So if you do have NX NASTRAN right now, it can be added on as the bundle NXN004, and it also is included in the advanced bundle. And if you have FEMAP with NX NASTRAN, it is an add-on E503. And here are the solution sequences that you get if you would step up to this dynamic response package. So a lot of people, instead of purchasing an individual dynamic response bundle, they would go ahead and step up to the advanced bundle. So one of the reasons why you would get the advanced bundle is including with the dynamic analysis bundle, you get aeroelasticity, DMAP, super elements, multi-step nonlinear, and you also get DMP, which is distributive parallel processing. Here are the solution sequence that you get with the advanced bundle. As you can see, you get some of the same that you got in the dynamics, except now we add those additional functionality. One of the bundles that you can add is rotor dynamics. So if you are doing rotating entities, this is a package to continue to step up past the dynamics add-on package. So if you are doing things like shaft turbines, propellers, you might be interested in the rotor dynamics. If you want to learn more about that, send us an email or a call and we'll get back to you on that. If you are using Simcenter instead of FEMAP as your pre and post, there is a response dynamic add-on inside Simcenter. So this is a graphical tool inside the Simcenter GUI to do force responses of a structure. So what it does, it allows you to evaluate the dynamic responses of the subject to various loading conditions. So it uses these responses based on modal approaches. So you would solve for your modal analysis, and then it uses these modal approaches to figure out these responses. So if you are doing dynamic analysis and you do have questions, you can always reach out to us. But if you have some internal questions, I definitely recommend checking out the user's guide. There's a basic dynamic, advanced dynamic, rotors dynamic, and even an acoustics guide. So if you are struggling or have some questions, how do these things come about, I would recommend checking out this PDF. So it is located in the root directory of NASTRAN. So at this time, I want to give a quick demo. I'm going to open up a little bracket with a motor on it. I'm going to solve for normal modes. Then I'm going to apply an acceleration of 1g to figure out the transient response. I think I have those backwards, and then I'm going to solve normal modes, transient response, and then I'm going to solve a frequency response. Yeah, these are backwards. Okay. So let me hop over into FEMAT, and here is my little bracket with a motor in it. So I want to go ahead and set this up for our dynamic run. So first thing that I'm going to do is take this motor and I'm going to represent it at the mass element. So to do that, I'll just hop over to Tools, Mass Properties, Solid Properties. I'm going to select my entity. And I'm going to create a node and mass element at that centroid location. So I'm going to enter in a density value. And in my case, I'm going to say that this thing is made out of steel. And I'm going to enter in a mass density of 0.00073. Now, one thing when you are doing dynamic analysis, please be careful with your units. Units can get into trouble. So just make sure that you are doing standard units and you are the same throughout your analysis. So don't mess with mass and weight. So make sure that you are consistent. So I'm just going to go ahead and hide these entities. I have meshed the bracket nice and clean. And now I'm going to go ahead and connect my mass element to the structure. To do that, I'm going to create an RBE3. So model element. I'm going to change my type to rigid. In this case, I'm going to do an RBE3 element. And for my independent nodes, I'm going to remove my rotational degrees of freedom. And I'm going to go ahead and select the nodes around these bolted regions. So easy way to select all these nodes around here is change my method to onCurve, and I'll go ahead and select them. It's easier if I turn on my geometry. And now I can select my curves. And the reason why I change it to this method, it's just much easier to select these curves and instead of individually selecting all those nodes with some of our pick methods. One thing that I like to do, I recommend, is hit this little highlighter. Let's confirm that we selected the correct nodes. And let's connect all these independent nodes to the center dependent node. I'm going to copy this node number so I have it later. So now that has linked the mass to the structure. Now I'm going to constrain the structure, but I'm going to connect both of these holes at the base of the structure. I'm going to connect them together in one central location to help me dynamically load this structure. So I'm going to go ahead and create this as an RBE2, and I'm going to select the nodes for the dependent entity same way as I selected for the RBE3. And just like before, I want to use my highlighter and make sure I selected all the correct entities. So now I have my model constrained. Well, now I want to set up a constraint at this base location. So let's go ahead and create a new constraint. I do this using the model info tree. Makes it easier for me, and I'll just call this fixed base. And in this constraint definition, I will select nodal, and I will define the center location. I'll fix it in all 6 degrees of freedom. So now I have the basic for a normal modes analysis. So I'm going to do a normal modes analysis, but I'm going to constrain it at the base here. So let's go ahead and create our new analysis. I right-click on Analysis Manage, select New, and I'm going to make sure I select Normal Modes, Eigenvalue, and I'm going to use NX NASTRAN as my solver. I'm going to select Next through a couple of these options. If you need to change any of your parameters, right here is the weight mass parameter. If you need to adjust weight and mass, this is where you would have to enter in a value. I'm consistent in my units so far, but if you are not, you would have to edit it there. So I'm going to use Lanczos, and I'm going to normalize by mass, and I'm going to request 10 modes out in this case. And in my case, I'm going to check modal effective mass fraction. I want to see the effective mass. In my case, I'm just going to make sure that I have the constraint specified. And if you need to specify other output, you can do that here. So let's go ahead and solve it, and let's look at the normal modes of the structure. So this should be done now. And now we can go ahead and look at our results. So here are our modes that it prints out. And this can be done in the base package. So everything that I've done now is in the base package, and then we'll step up to the dynamics package. So we can go ahead and review mode shapes. One mode shape I want to look at is mode 5. So you can see the structure is moving in the y direction, so this mass has a lot of motion in here. So I requested out these mass fractions and the sum. So I'm going to visually plot this effective mass here. You can just select what you want, right click and show, and it'll bring it to the charting plane. And just based on this, I can see that right here at my output set number 5, all this mass in my T2 direction, which is this, is moving. So it wasn't moving in the other ones, but once I hit this, you get this big mass participation. Same thing, if I look at mode 2, you'll see in the T3 direction, I get this big participation in the second mode. So if I just pop over here, we'll look at mode 1 is showing that T1 has a large value. So we'll start at T1. Mode 1, you see it's moving greatly in the X direction. Then T2, it starts to move in this Z direction. So it's a good way to review our modal results, check masses moving in certain directions, and go from there. So now that we have our baseline normal modes run, normally I recommend running a static run just to give you a baseline before you step into dynamics. I did that beforehand. I'll just give you the pertaining information when we get there. But that's another thing that I recommend, running and testing to make sure before you step up to your dynamics. So in our case, let's go ahead and step up to a frequency response. So if you remember, frequency response is based on a frequency. So let's go ahead and apply a load. So in this case, I'll just call this frequency. And inside our load, I'm going to apply a acceleration to this base node. Now, it might seem, I guess, odd that we are applying a load to a place that is constrained. NASTRAN will change that in the deck so that it will work for us then. So in our case, let's go ahead and specify acceleration, and I'm going to accelerate at 1g, which is 386 in my case. Now, we need to create a couple functions. So I'm going to remove the functions that I already have just to clear up some clutter. So let's just right click on functions new, and I want to create a function for structural damping versus frequency. So I want to define some damping of the structure. So I'm going to give it, so I'm going to say at a frequency of 0, we have a damping of 5%, and then I'll say at a frequency of, 5,000, we have 5%. So now I have 5% structural damping throughout the frequency range. Now, what a lot of people do here would be to create another function versus frequency, and this would be reference to our results. So this would be where we want our sweeping 1G sinusoidal load to go at. So most people would specify a band around their frequencies. So you would do normally a linear ramp. So you'd say maybe 1 through, we'll just say in our case, 350 hertz. We want delta 1. So we want our input to be at each one of these individual locations. And then you could say 350 to, I'll just say 600 in this case. We want our delta to be 10. So it's not giving us output through all those regions. And you would continue to go through all of the modes in your model. Now, I'm going to show you a different way to define these frequencies. You can even create freak cards as well, which we'll talk about shortly. We just want to define where these frequencies are being input. So I'm going to show you a different way. I'll just hit OK for now. So that is one order of operation. So now that we have our function defining for our damping, we have our input function, which we just created. Let's go ahead and create a solution. So we'll create a new solution, and we'll hop over into frequency harmonic response. And we'll go to our dynamic options, and we want to do a modal analysis type. And inside here, we need to make sure that we link to the damping table, so structural damping. And right here is where if you wanted to define your frequency cards, and that is for your frequency response, we can link to that function that we created earlier, or there's a nice button here for modal frequencies, which will give you a band that is 5 points per mode, and it goes 10%. So it goes above and below this mode value, so it gives you ranges right around the modes. It's a way to get, I guess, less information out of your model around these bands. You can change these values if you want more information around the modes. So now let's just make sure that we have our constraint, we have our load, and whatever we want as an output in this case. So now we can go ahead and solve our model. So this should be done shortly. There we go. And now we have our output. So real quickly, I want to show you that modal frequency table. So it just shows you peaks around those modes. So it just fills out this table for you so you don't have to define it where we were defining our other function in that region. All right, so let's go ahead and look at some of the output that we have. So let's pop open our charting window again. I'm going to delete all the output that I have here. Let's create a new data series. This form is a little bit different in FEMAP 11.4, so we'll change it vector versus set. We want the output set value, so I want to know the value. And now this is a nice thing with studies is I can say, hey, I want the frequency analysis set, and it'll grab me the starting and the ending. In this case, I want to know T2 translation of this mass element. So how much did this move in the T2 translation? So now I can visually see what went on. Now, these values are, they appear to be extremely small. My structure is a little too stiff here, made it out of steel. But this value is 20 times higher, 20 times magnification of my static run. So it's at these frequencies, it is being excited 20 times my static run. So we are seeing this large increase in dynamic loading. So one of the nice thing that I like to do if I have these results is hop down here to my study, my frequency analysis. If I just right click, I can envelope these on the fly and say maximum value. And it's running a calculation where it's enveloping all those outputs to a maximum value. And once I get maximum value, I can go ahead and post-process. So now I have max. So if I hop over here to post-processing, I throw a contour plot. This I'm showing stress. I can visualize our stress values of my structure. But what I like to do is the next one, which is the envelope set info. So I can visually see, and in my case, most of my structure is all coming from this load set number 32. So this is plotting the set number. So if I was interested in the middle of this entity, I would want to look at my set number 45, but maybe I'm interested in the rest of the structure. No, case number 32 is showing me, it is giving me the max values. So in our case, let's go ahead and pop over here and let's look at what is set 32. So if I go back and we go find case 32 here, that's at 290 hertz. If you remember, our original frequency around 290 hertz is where all that mass was moving down in that y direction. So using simple enveloping of the output, we can clearly see that has happened. All right, so let's hop over to a quick transient analysis. So for this, I need to create a new load, and this is with time, since we're hopping into transient. Our load definition, I'll say nodal, and I'll apply it to that same location. This time I'm going to apply a displacement, and I'm going to say in the y direction, let me give me 1 times some sort of frequency dependent, this time it's time dependent function. So I'm going to define my pulse. So I'm going to basically displace this thing at a period of time, this 1 unit. So in my case, I need to make sure it's versus time. I'm going to give it a single value. So I'll say at time 0, I have 1 of those loads. And then some time down the line, I still have that load. And then some time right after that, my load has let off. And then I'm going to continue that till the end of this chart. So we're just going to impact it with this load from the bottom that's going to push it 1 unit, which is 1 inch in my case, for a short duration of time. So my load is 1 times that. So now I have this input of that load. So let's go ahead and set up a transient analysis here. So let's create analysis, new, change my analysis type here to transient. And let's go ahead and make sure that we have our correct parameters. So in my case, I'm going to do a modal method again. And I'm going to enter in a equivalent viscous damping of 0.05%. And frequency for system damping, I'm going to enter in a value that's very close to my original first mode. I'll just put 80 Hertz. And now, since I am doing transient, I need to enter in these time steps. So I'm going to say I want 70 steps. Each step I want to be 0.005 seconds, and I'd like output at every one of these output times. This way I can see what's happening at impact and then after. Okay, so it looks good. Make sure you have the correct load with time. Okay. And if you want any other output, you can specify that. So now I'm going to go ahead and solve this solution. And this should only take a couple seconds to solve. All right, now I have output. And just like before, let's go ahead and graph our results, and we can see visually what's going on. So I'm going to delete this one that exists. Create a new data series, vector versus the set. I want the set value. So I would like to know, and once again, this is great where studies can go ahead, grab this transient case, start at the beginning, end at the end. I want to know the total translation of this node. And now I can see this node. So we can see we started out at 0 seconds, we displaced it 1 inch, and then it, due to the impact, it continued to move in that direction, and then it oscillated back, and then you can see it has damped out of the structure. So you see how much damping really plays effect here. So this would oscillate a lot more if we had less damping in the structure, or we had more damping, this would damp out much quicker. So one thing that I like to do is use my little entity selector, go ahead, grab my node, select it, and if we do have post-processing information, maybe I'm over here and I want to plot a contour plot. In this case, I want to know total translation, and I want to know it at, maybe the last second of time or at impact. I can go ahead and do that. So you see we have all these points in time. But let's go ahead and specify at 0.0025, 0.025, sometime after it has impacted. And let's look at our total translation. So now I can visually, if I have my little selector and I click here, using my entity info, I can see the total translation over here of that entity. So I can see after X amount of time how much it translated. I can envelope and figure out what's the max value as well. Or maybe I want to know at impact, I can change my output set to whatever case that was. So I have full control over what's going on. So at impact, I can visually see the total translation of those. The base, as you can see, was moved 1 inch. That caused a translation of this guy to move 0.78 0.78 of an inch. So using transient analysis, we can go via time and see what's happening to the structure. So I know that was quick through simple dynamic analysis. Dynamics can get really far in the depth. I just wanted to at least show you guys a quick model that goes through frequency response, transient response, and even a simple normal modes analysis. So I hope I gave a good overview of the Dynamics add-on in NASTRAN, what's included, the solution sequences. I know I went fast through that. I wanted to at least include it in the slide deck for reference. If anybody wanted to go back, then I at least have it. And then hopefully my demonstration showed you that, you know, setting up these analysis inside FEMAP isn't overly difficult. Setting up the modal analysis, setting up frequency response, and setting up a transient response. The one thing to remember here is frequency response, we're in the frequency domain, transient response, we're in the time domain.
Great. Thank you, gentlemen, for an excellent presentation today. And to our attendees, we will be posting this video to our YouTube channel later today. Feel free to pass along to your friends and colleagues, and please be sure to subscribe to our channel. Follow us on Twitter and LinkedIn for upcoming webinar dates and topics. And please, if you could just stick around for 10 to 15 seconds afterwards to fill out our survey, let us know how we did and what you liked. We really appreciate your feedback. And thank you again so much, everyone, for attending. Have a great rest of your day.